You know that feeling when you're staring at a math problem and you know how to solve it, but man, the process is just so long and boring you can barely bring yourself to start? We're talking about raising something simple like x plus y to a really high power. Well, today we're going to pull back the curtain on an absolutely beautiful mathematical shortcut that turns hours of painful work into just a few simple steps. Let's dive in and find the elegant pattern that makes it all possible. So, take a look at this. We've got x plus 2y raised to the 16th power. I mean, just let that sink in for a second. How would you even begin to tackle that? The straightforward way seems, well, it seems like a total nightmare, right? You could literally multiply x plus 2y by itself, then take that huge answer and multiply it by x plus 2y again and again 16 times. Not only would that take forever, but let's be honest, the chances of making one tiny little mistake somewhere in that mess are, like, basically 100%. But what if I told you there's a hidden pattern baked right into this problem? A secret structure that once you see it, lets you jump straight to the answer without all that grunt work. This is where math stops being about calculation and starts getting really, really cool. So how do we find a shortcut for a monster problem like that one? Well, like with most big problems, we start small. We're going to go on a little pattern hunt by looking at much simpler versions, like raising a binomial to the second, third, or fourth power. So here they are, all worked out for us. We've got powers of 2, 3, and 4. Just take a look. Don't even worry about the numbers in front yet. Just look at the x's and y's and their little exponents. Do you see anything happening? Some kind of rhythm? And what about those numbers in front, the coefficients? If you stare at it long enough, two really clear patterns just pop out. Okay, first, the exponents. Notice how the power of x starts at the max and then drops by 1 in every term, all the way down to 0? At the exact same time, the power of y does the total opposite. It starts at 0 and climbs up. And check this out. The exponents in any single term always add up to n, the power we started with. Then you've got the coefficients. They form this really clean, symmetrical pattern. For the fourth power, it's a perfect 1, 4, 6, 4, 1. Now, this isn't just some random coincidence. Oh no. This is one of the most famous patterns in all of mathematics. It's called Pascal's triangle. And this amazing thing holds the keys to the coefficients for every single binomial expansion you can think of. And what's so wild is how ridiculously easy this triangle is to build. You just start with a 1 at the very top. Then, every new row you make starts and ends with a 1. And here's the magic. Every other number is just the sum of the two numbers right above it. See? 1 plus 1 gives you 2. Then 1 plus 2 gives you 3. It's that simple, and it just keeps going, generating all the coefficients we could ever need. Okay, so we see the pattern. It's cool. But why does this simple little addition trick actually work? I mean, what's really going on here? Well, the answer takes us a little deeper, into something a bit more formal. It turns out every number in Pascal's triangle is what we call a binomial coefficient. And this is where it connects to another big idea in math, combinations. The notation, which we read as n choose r, is all about counting. It tells you how many different ways you can choose r things from a group of n things. Now, why does that matter for our problem? Well, think about expanding x plus y to the fourth power. That's really just x plus y times x plus y times x plus y times x plus y. To get a term like x squared, y squared, you have to choose the y from 2 of those 4 parentheses, right? The formula 4 choose 2 literally tells you how many ways there are to do that. That's why it gives us the coefficient. And the n factorial in the formula? That's just a factorial. You just multiply that number by every whole number below. And here's where it all clicks. This table just lays it out perfectly. The row for n equals 4 in Pascal's triangle, that 1, 4, 6, 4, 1, lines up exactly with the calculations for 4 choose 0, 4 choose 1, 4 choose 2, and so on. They are just two different paths to the exact same numbers. And this is huge, because it means we can now find any coefficient we want with a formula, without having to write out the whole triangle. All right, we've cracked the code for the exponents, and we've decoded the secret of the coefficients. Now it's time to put all the pieces together into one single powerful formula. This right here, this is the master key. And this is it, the binomial theorem. Now I know it might look a little intense with that big sigma symbol. That's the Greek letter sigma, and it just means add everything up. But don't let it scare you. All this formula is doing is putting the patterns we just discovered into a neat little package. It's saying to get the whole expansion, you just add up a bunch of terms. For each term, the coefficient is n choose k. The power of x is n minus k, and the power of y is k. That's it. It's the complete blueprint. Okay, let's see this thing in action. We'll expand 3x minus y to the fourth. First, we identify our parts. N is 4, our first term is 3x, and our second term is negative y. Gotta watch that negative. We grab the coefficients for n equals 4, 1, 4, 6, 4, 1. Then we just assemble the puzzle. We combine the coefficients with the falling powers of 3x and the rising powers of negative y. We clean it up, and bam, there's our final answer. And notice how that little negative sign makes the terms flip-flop between positive and negative. Pretty neat. So expanding the whole thing is really cool, but the theorem has an even more powerful trick up its sleeve. See, sometimes you don't actually need the entire expansion. Sometimes you just want to find one specific piece of it. Let's go all the way back to that monster problem from the beginning. What if we don't care about the other 16 terms? What if the only thing we want to know is, what's the 10th term in that gigantic expansion? I mean, calculating all 17 terms just to find one of them sounds like a colossal waste of time. And you'd be right. Luckily for us, we can pull just one slice out of the binomial theorem to create a formula for any single term we want. Think of it like a surgical tool. It lets us go in and pluck out the exact term we need, leaving the rest behind. So how do we use it? Well, for the 10th term of our big problem, we know n is 16. Now here's the one little tricky bit you gotta remember. The first term uses r equals 0, the second uses r equals 1, so the 10th term is gonna use r equals 9. Once we have that, we just plug n equals 16 and r equals 9 into our formula. Now all that's left is to punch 16 choose 9 into a calculator and simplify the rest. And there it is, just like that. The 10th term is 5,857,280 times x to the 7th power y to the 9th. We found it. We used a laser to find one specific piece of this massive puzzle without having to do any of the other work. So let's just pause for a second and appreciate what just happened. We took a problem that would have been an absolute nightmare of manual algebra, pages and pages of it, and by understanding the pattern underneath, we turned it into a quick, clean, three-step calculation. That, right there, is the power of the binomial theorem. Ultimately, this isn't just about algebra, is it? It's about a whole way of thinking. We took something that looked messy and complicated, and we found a hidden structure that made it simple. It really makes you wonder, doesn't it? What other complex parts of our world are just hiding a simple pattern, waiting for someone to find it?